Okay, there, we're recording, it's official. Welcome back, the few, the proud, the people who are well enough to attend class. We have the invariance unit to wrap up today, which is going to include the remainder of lecture 7, as well as example 7C, and if time permits, 7D. If we don't get through 7D, then I will make a little video about it and post that separately, because after break, I want to be able to get into higher order factor models, method factor, bifactor, all that kind of stuff. Basically, how do we address multidimensionality, whether it's intended or unintended, and then the grand finale would be the SEM. So the good news is that you've already learned the hard part. Honestly, if setting up the measurement models and going through that process of making sure they actually fit, that's where the work is. Once you actually get all your latent factors built, sticking them in one model and letting them predict each other is relatively straightforward. The structural model will have very few degrees of freedom, so you have very little room to be wrong in most cases. So that's where we're headed. In terms of work, so let's see, homework 5 is due after break, which is run your own IRT and IFA models on your own data. So it should not be, if you've already done homework 3, then you've done a lot of the work already because you already have the code, you've already wrangled the data and all that stuff. If you run into estimation problems, please let me help you. It may not be possible for everyone to end up using maximum likelihood, particularly those of you with small samples, so I can try to help you simplify or estimate or introduce start values or other kinds of tricks that we haven't had a chance to talk about as a group. Any questions on homework or otherwise? No? Just as an FYI, next week, since we're not having classes, I'm not having office hours, but I will be on email if anybody wants to contact me that way. During finals week, we're not meeting, but I'm having office hours. So my plan during finals week is to have my regular office hours on Monday and Wednesday at 3:30, as well as to be sitting on Zoom the whole time I would have been teaching on Tuesday and Thursday. So 12:30 to 3:30, Tuesday, Thursday of finals week, I plan to be on Zoom in case anyone needs some last minute help getting everything caught up by the end of the semester. Then we will all be done. Hooray! So that's the good news, is that whatever stress and overwhelm you're feeling right now, it will not last forever. One way or the other, the semester will end. And then we can breathe for a few weeks until it's time to do it all over again. On that happy note, let's talk about diff. So I'm on slide 24 here. Other than some new terminology, you've already learned this. This is measurement and variance testing on models for binary or ordinal data. So the terminology switches, but the intent is the same. So previously what we called measurement invariance has an inversion in how we talk about it. The term differential item functioning is non-invariance. So if the item parameters are different across groups, occasions, or conditions, whatever you're testing invariance across, it is called diff. So diff for difference. So an item is said to have diff, and yes, that is the acronym that the entire world has agreed on. You can call it diff. People will know what that means once you've defined it once. An item has diff if people with equal amounts of a trait, but from different groups, have different expected responses. So the idea here is still that the only reason why people answer the questions the way they do is supposed to be their trait. And if their response is separately related to their group, that's a problem. That means that there's something else that's causing them to respond the way that they do that's related to the group they're in. It's not related to the trait because we will have already controlled for any trait differences. And just as we had for CFA models, we want to make sure that we have at least partial measurement invariance. Most of the item parameters ideally would work the same way. That way we have confidence that we're actually measuring the same trait in both groups. So just as we did in CFA, if your groups are independent, then you want to do a multiple group model. So that would be separate but simultaneous models where we would successively apply a series of constraints. If your groups are dependent, so like a longitudinal study, partners from the same relationship, parents and children, anything to where there's a relationship between the kinds of factors, that goes into the same model instead. Like the example that we just did on Tuesday of longitudinal analysis. So in the IRT literature, diff is a big thing. It's big with respect to not just educational testing, but also the uses of IRT models in other fields as well. Terminology that you may see in that context is uniform diff versus non-uniform diff. Those of you who had the IRT class previously, those words sound familiar? Yeah, so they're still using those words. It's not out of date yet. That's good. So uniform diff refers to the idea of the B parameters being different. So the item location is different. The amount of trait that is needed to have a 50-50 probability of the higher response, so that could be just a 1 instead of a 0 for binary models. The higher of the two choices for the submodel when we're talking about ordinal, so like 0 versus 1, 2, 3, 0, 1 versus 2, 3, 0, 1, 2 versus 3. This would be the amount of trait that it takes to have a 50-50 shot of answering the higher of the two choices. So for example, if I had an item like how often do you cry, and it was supposed to measure depression, would men and women potentially with the same amount of depression have the same expected item response? Or I can imagine that women might say that they cry more often, and that may or may not be true, but women might be more willing to say that they cry more often because there are not as many gender norms associated with crying in women as there are in men. So there may be other reasons besides the trait why people would answer the question differently, which then trickles down to their item parameters. Non-uniform diff is analogous to metric non-invariance, where both the A parameter and potentially the B parameters would differ. So the slope is different in that case. So the item is more discriminating in one group than the other. The other step, so we have analogous to scalar, analogous to metric. What about residual variances? Now it depends on your estimator. In full information maximum likelihood, there is no residual variance. It's just, well, it's 3.29 if you're in logits, or it's 1 if you're in probits. And if there are no estimated residual variances, then we can't test whether they differ across groups. It's not a parameter. However, in WLSMV, so in limited information diagonally weighted least squares estimation, after you constrain an item's loading and thresholds, it is possible for a separate residual variance to be estimated in the alternative groups. It doesn't really mean anything, but it is possible. So I'll show you how that works to be able to test that, because that step is backwards in terms of the order, because you have to keep everything fixed until that point, at which case then you can free it once you have constraints in place. So the same thing in pictures. This would be an example of uniform diff if I have the same item for two different groups. The amount of trait that is needed to hit the 50-50 mark depends on which group you're in. So the green group needs more theta to be able to get to the same probability. Non-uniform diff would just be different slopes. And if the slopes are different, potentially the B parameter might be different as a consequence of the different slopes. So same ideas. If the slopes are different, that means the item is less related to the trait in one group than the other. If the B parameters are different, that means that the item is easier or more difficult in one group than the other. Easier to endorse if it's not an achievement type of item. Okay, with me so far? So then for categorical outcomes, and this is how it would work in M+. So there's two different versions of the model. As we've discussed, there's the IRT version and the IFA version. In M+, what is estimated directly is the IFA version. So you get stupid thresholds and you get loadings. And if you want to, you can figure out what the corresponding A and B would be that goes with them. But what is estimated directly are the item factor analysis parameters instead. So when M+ does multiple group models, it converts to the IRT parameters A and B, but it does so after rescaling the trait. So the implications of this is that because the conversion from loadings and thresholds into A's and B's requires the factor mean invariance, even if your loadings are invariant, your A's won't be. Even if your thresholds are invariant, your B's won't be. So just to remind you, here's the formulas that we get using the theta parameterization, which is a probit scaling to go back and forth. So if you have the loadings, like right here, if these are constrained equal across groups, if the groups have different theta variances, their A's are going to be different. Likewise, for the translation into a threshold into a B, if the groups have different theta means and theta variances, the thresholds in loadings could be invariant, but the B's aren't going to be. So this is to say we're testing invariance of loadings and thresholds. We're not testing invariance of A's and B's and M+. If it's important that you test A's and B's directly, then you're going to have to find software that estimates it in A's and B's to start with. Does the R package MERT do invariant stuff? Does anybody know?
Yeah,
kind of.
It
It has a diff function?
Yeah.
Okay, so you can use the MERT package if you can figure out how to use it. Not it. Not adding that one to my list. So I will show you how to do the loadings and thresholds, basically, but just know that the A's and B's are going to be non-invariant if the trait mean and variance differ. So in the examples that I'll show you, I'm going to basically pretend there's no trait differences in the alternative group so that I can show you what the impact of the diff would be in A's and B's controlling for that potential difference in scale. All right. So to do invariance testing in M+, the code looks different if you're using WLSMV than if you're using maximum likelihood. If you're using maximum likelihood, you have to trick M+ into thinking it's doing a mixture model. So mixture models, or latent class models as they are known, so latent profile, latent class, mixture models, trying to think of other synonyms for those. Those are designed to find hidden groups. You have to pretend like you have hidden groups, but that you know what they are in order for this code to be executed. Question from the Zoomers: do you think this is where some companies will state one over another to make their assessment or test seem like bias is not present? That's an interesting question. It would be hard to make that argument to say that, like, the A's and B's are fine, but the loadings and thresholds are not fine. I wouldn't buy that argument. But perhaps someone who's reading the documentation who's not as familiar with these conversions might be swayed. I don't know. That's an interesting question. What I do know is that the code looks different. So you have to hack the mixture model thing here for maximum likelihood. In WLSMV, it looks a lot like what we've been doing with the grouping variable. And diff test is used to do likelihood ratio test equivalence. So it's not a likelihood ratio test, but it is a chi-square difference test done for you. As long as we have the theta parameterization, we can eventually test differences in residual variances. Now, one thing that you should also be aware of, ... I'm going to answer a question first. Could we test diff when we generate A's and B's using the model constraints? Theoretically, yes. So the A's and B's are going to differ even if the loadings and thresholds don't, because if you let the theta mean and variance differ. But I think in theory, like, you could still write a linear model basically for the difference in the A's and the B's across groups, and maybe ask for that as an additional computed quantity that you could make a hypothesis test about. Alternatively, it would be a lot of work, but I think you could do it, is to set up the model with the loadings and thresholds, but then using constraints, create the diff tests on the A's and B's instead. I can see how that could be done. I don't have an example of it, but I could probably help you figure it out if that was something that you wanted to do. It basically would be analogous to when people want to put constraints on standardized parameters. So in the results, all you get are unstandardized, right? But if you wanted to test, say, whether a residual correlation differed across groups. Not the covariance, but the correlation. What you would have to do is create the correlation as a new parameter using labels on the covariances and variance, and then put a constraint on that new parameter and test it against groups. So yes, I could see a way it could be done on A's and B's, but not easily. You'd have to do some work, extra coding for that. Thanks, you're welcome. Now what I was gonna say, here's where this process for ordinal data breaks down. If you have a different set of answered responses across your groups, so let's say that you have a 5-point Likert scale, 1, 2, 3, 4, 5 in group A, but group B only gave 1, 2, 3, 4. Nobody in the second group picked 5. Could that happen? Sure, why not, right? Especially if the groups differ in like their severity of the trait, right? Maybe group B has less of the trait, so no one needs to pick 5. If you try to do invariance analyses with different possible numbers of submodels, M+ will yell at you and not do it. It's not built for that, not in WLSMV. So if you wanted to use limited information to do this type of invariance testing using ordinal models, you would have to recode the data so that each group has the same number of categories used. In my example, if group A answered questions in category 5 and group B didn't, you'd have to turn all of those 5s into 4s. Then each group would have a scale of 1 to 4, and then you could do it. So that is dissatisfying. To get around it, you could use maximum likelihood instead, and I do have examples that I could send anyone who's interested as to what the code would have to look like. But you'd have to go through and essentially relabel the thresholds to make sure that if there's any missing in the middle, like they're not counted under the wrong one. So it takes more code, but it is possible to have different response options, but it's just not done in WLSMV. So the same configural model that we would use as before, where we would fix the factor means to 0, fix the factor variances to 1 for identification, free all the loadings, free all the thresholds, and if we're in WLSMV, we'd have to start with the residual variances all fixed to 1. Then we would do metric, then we would do scalar, and at each stage use diff test for the nested model comparison. However, the M+ creators do not recommend it this way. In their examples online, they lump together steps 2 and 3, and they test invariance of the loadings and the thresholds at the same time. The rationale for that is that those parameters are related to each other, so they should be tested at once. Jonathan, for instance, thinks it should be done that way, and if you learn these models from him, that's the way he would do it. I disagree. My logic is that if they have to be tested together, then uniform diff in IRT would not be a thing. Because uniform diff means only the B parameters are different, not the A parameters. How would you know that if everything is tested together? So if you believe uniform diff could be a thing, then you're saying, I think it makes sense to separate out the test of the loadings from the test of the thresholds. Reasonable people may disagree. In the logit or probit space, it is a linear model. The slope is linear. So I think it makes sense from that perspective in the same way that it makes sense in CFA with a linear slope. All right, let me show you what this might look like in an example. So I want to pull up 7C. These are the same data that you've already seen in example 6A. These are the 7 items of independent living in older adults. Now we're using the same data set to look at diff across men and women in my sample. So I have the frequencies of the responses in each group here. So this is something that you would report, as a descriptive statistic as part of an article. in the code, it looks a lot like the CFA examples for multiple group models would be. So here's the one thing you need, grouping, where you tell it which column of your data set holds the grouping information. So the column in this case is called female, and then I attach the labels here in the code. That way when I get my output back, it tells me who the model is for, not just group 0 or group 1, but with the labels. The other piece that you would want to remember to start with is on the save data here to ask for the diff test to be saved. So it's saving the information from the configural model in preparation of using it to test metric invariance after we constrain the loadings in a subsequent step. So just as we had for our multiple group example in CFA, we have a model, which is for the reference group, and then model alternative. So previously I had the women as the reference. Now I'm switching it up to have the men as the reference. So this is a binary group example. I have labels here, so L underscore I1 to L underscore I7. The L stands for loading, the I stands for item. I have all of the thresholds written out, and fortunately in my case, all 4 categories were observed in both groups, so I don't have to worry about rounding my data into convenient bins. I've got my thresholds labeled, but they're not constrained yet. These are just labels. The residual variances for my 7 items, categorical items, that's what the C means, is fixed at 1 for identification. And likewise, the factor mean and variance are fixed to 0 and 1 respectively for identification as well. Then if I come down to the model for women, it is exactly the same. The only thing that's different in terms of the code is the lack of labels. So I don't have any labels on the bottom here. That means they're all separate. So the process of constraining them to be the same will rely on attaching each of these labels in successive models, which then will make those parameters the same between men and women. All right, with me so far? Question?
Yeah, can you say it again, like what you just said?
Yeah. So I was pointing out that all of the parameters that we're eventually going to constrain are labeled in the men reference model. This code is going to stay the exact same the entire time. What's going to change is layer by layer, we will attach the same labels used up here in the reference group to the alternative group. And once the same label is used in both groups, the parameters are constrained equal across groups. But right now, because none of these are labeled, they're not constrained equal. Everything is separate. So we're fitting a single factor model separately in men and women, but simultaneously, so that we can use its combined fit as a baseline for judging decrements to fit after applying constraints. So then chi-square test of model fit is significant, meaning our model's not perfect. However, the rest of these fit indices look pretty good. RMSEA is a little bit high, but CFI, TLI, SR, MR are all pretty good. Note the chi-square contribution from each group here. So the contribution to the 72 is about 25 of it came from the men and 48 of it came from the women. Now, can I draw the conclusion that the model for women is more misfitting than the model for men based on these chi-square contributions? Can I say that the women's model fits worse than the men's based on this? You're shaking your head no?
No.
Why not? Because you're right. I can't say that. I can't look at these numbers and say, oh, the model fits worse in women because their chi-square contribution is higher. Do you know why their chi-square contribution is higher? There's more of them. That's why. There's 420 women and only 214 men. Because people in their 80s, that is the gender balance at that point. Men tend to die sooner than women. So our study has a lot more women in it, and that's why the chi-square contribution is higher. What that is also going to mean is that any parameter that is constrained equal across the groups, it's going to look closer to what the women's version would be because the women outweigh the men. So our configural model then fits reasonably well, which means it makes sense to go forth and test if the parameters differ across groups. So here's my picture of the loadings. The loadings are not on the same scale, but do you see items that look like they're sort of different? So like 1 looks pretty different than the rest of them. 3 and 4 look a little different. So this is foreshadowing. So here's my solution for the men as the reference over here. The alternative group is the women's over here. Do we need to review what the parameters mean? Would that be helpful? So factor loadings, those are still slopes, but they are the change in the probit in this solution for a 1-unit change in theta. So everything is in probits. These are z-scores that correspond to the predicted probability for the area to the left under a standard normal distribution. Theta has a mean of 0 in both groups because it's identified that way. Stupid thresholds, these are the expected probit of y equals 0. So the lower answer for each of the submodels when theta equals 0. So these are indices of difficulty because they tell you what is the probability of not being able to do it. Variance of theta is fixed to 1 in each group for identification, and residual variances are all fixed to 1. They have to be at this point. They're not separately estimable. So then metric. The difference in the model code is right here. So I've applied the loading label to the alternative group. So because the same labels are being used in both groups, that's constraining their loadings to be the same. What's the other thing that I have to do once I constrain loadings? What do I got to free?
Factor variance?
Factor variance. Yes, comment from the Zoomers, genderedized tasks. Yes, they are indeed. Stay tuned for that. There's a quite ready explanation for the pattern of diff here. But yes, right there. I also had to free the factor variance in the alternative group because one of the reasons why the loadings may have been different is that the factor variances are different. So we're testing to see if they are proportionately different as a consequence of factor variance differences. The other thing that you will need to do, and this is easy to forget, is to keep switching out these diff test lines. So what goes in save data is your current model's name. So I've called this metric A. What goes in analysis is the previous model that you want to compare against that had more parameters. So the configural model is the comparison. Metric A is being saved for a further potential comparison. So our new model still doesn't fit perfectly. Oh well. Here's my diff test for invariance. So p-value is 0.15. It looks like I can constrain the loadings and have it be reasonably okay. 6 loadings, degrees of freedom 6 because it was 7 loadings minus 1 factor variance. However, if I look at the modification indices, item 3 is responsible for the majority of the chi-square difference. So this is another point where people would reasonably disagree. But to me, knowing that most of the misfit that I've accumulated is in one spot makes me want to not hold that item constant. So I decided to let item 3's loading differ. And I did that by changing the label here. I stuck a W on it. So item 3's loading gets to be different between women and men. So now I'm saving the results as metric B, still comparing against configural. I have an example of how you would reverse the process to see if you're headed in the right direction. And so yes, freeing that one loading did help us. So here's the end result now, our chi-square for difference testing, more non-significant before. None of the individual loadings were highlighted. So yeah, that one, now it's happy. These are the thresholds. So the difference in the patterns is the gender difference here. And it looks like for, say, item 3, that one looks very different in terms of the men's being much higher than the women's. Item 3 looks very different sort of from all the others just across the board. So I would expect that one to be potentially problematic. So the end result then of item 3's loading being different across groups is right here. So the loading is 3 something in the men and it's 6 something in the women. So how would I describe that in words? Go for it.
I would say that comparing women with men, in women, this item is more related to the latent factor than in the other one.
It's more, yeah, it's more discriminating, has a stronger slope, is more related. Do you know what item 3 is? Cooking. Being able to cook or not is a stronger indicator of being able to live independently if you're a woman than if you're a man. Keep in mind that these people are in their 80s, and these data were collected probably in the 90s. So these people were born around 1900. During that time, it may not have been as emphasized that men learn how to cook as it was for women. Clearly, times have changed. Me being, case in point, I don't cook, I can't cook, I don't want to, I'm bad at it, and you can't make me. Jonathan does the cooking. We have a division of labor with respect to our son. He keeps him fed, and I keep him clean and in clean clothes. And that's how we do our parenting. So, I don't cook. I am the exception to this rule. But cooking is more important in women than it is in men. So we let item 3 have a different loading. I'm going to then move on to test thresholds. Because I only have 7 items, I'm going to see if I can hang on to the thresholds for item 3 anyway. I'm not going to kick it out of the tournament yet. So here's a trick you're going to like. On page 6, do you see what this says in the comment right here, followed by the blank spot? Item thresholds are now constrained equal to men by omission. There are multiple different ways in the code to enforce invariance. Applying the same label is only one of them. The other way you can enforce invariance is to just not mention a parameter in the other group, and it's assumed to be invariant. So by not typing anything, I have made the thresholds invariant. So I'm comparing this scalar A against my prior metric B. Way significant, so I'd go through the process of trying to figure out why. In this case, the modification indices, the ones that I want to focus on, are going to be related to the thresholds that I just constrained. And sure enough, threshold 3 of item 3 wants to be different between the groups. So that was the last submodel for the cooking item. And because I already knew this was going to happen, I went ahead and freed all of the thresholds for item 3, not just the third one, but all of them, because it had already failed metric invariance. So then I list just those 3 thresholds in the code, which makes them different. Factor mean, by the way, is now estimated at this stage. Diff test says, nope, still significant. Okay, back to the modification indices. Threshold 3 of item 1 wants to be different. Okay, let's try that. This is scalar C. compare it against metric B. So I'm adding the third threshold for item 1. Diff test still significant. Okay, item 2's threshold 3 wants to be free. All right, we try that one. Close to not worse. Keep going. Now it's item 1, threshold 2 wants to be free. So now we're up to this many non-invariant parameters. Finally, the diff test says it's not worse than metric, and scalar is done. So it looks like out of the potentially, let's see, 21 thresholds, because I have 7 items and each item has 3 submodels, I had to give up 6. So 6 out of 21. 6 out of 7 loadings are invariant, and 15 out of 21 thresholds are invariant. So here's my solution. I've highlighted in bold the ones that are different. Not quite done yet. The next step is potentially to test residual variances. This is the part that you can only do in WLSMV. So it proceeds backwards. Up to this point, the residual variances were forced to be equal to 1 in both groups because they weren't separately identified. Now, for every item that has full invariance for its loadings and its thresholds, I can separately estimate a residual variance in the alternative group. It's identified at this point. So I have to first estimate a model that has all of those residual variances free as a comparison, and then re-estimate the previous scalar model against it, because diff test always goes in the order of more parameters than fewer. So the @1 holds the residual variance equal to 1 in the alternative group because for item 3, its loading and all 3 thresholds were different, and so that item's residual variance is not separately identified, but it is for all of the others. So we estimate this model just to get the chi-square for it to be used as a comparison. Then we go back to re-estimating the model that we had before for scalar. Diff test says almost not worse. Modification indices say that item 2 and item 7 want their residual variances to be different, so I tested those in sequential models, saved you a step, and this is where we end up with. So item 1, 3, 4, 5, 6 are all equal, and 2 and 7 want to have different amounts of residual variance in the final solution. Diff test says that's fine. Last step is factor invariance. That diff test was significance. So now we say, nope, the factor variances need to be different, and so do the means. So here's my solution. So item 3 is cooking. And the conclusion that we would draw about the pattern of diff is the same. Cooking is more discriminating in women than in men. Okay. Now we go down here. Item 1 is housework. The thresholds for men for threshold submodel 2 and 3 are different than for women. How would I talk about that? Which group has the more difficult thresholds? Housework is more difficult for whom?
Women? Or is that backwards? Thresholds.
Thresholds are indices of difficulty. So a higher threshold means it's more difficult. Now these are negative numbers.
Not in absolute value, but in actual.
Yeah, in actual value, not absolute value. Yep, in men. -4 is greater than -5. So what a threshold is the probability that you can't do it. Okay, it's the probit that goes with the probability of the lower answer conditional on a theta of 0. So housework is more difficult in men than women. Bed making, at least the last threshold, also more difficult in men than women. Yeah, and I'm going to cry bullshit on that one. I can't make the bed, honey. Sorry, it's really difficult for me. Yeah, no. That's like me. I don't know how to run the lawnmower. We have a riding lawnmower at our house, and I don't know how to drive it. I'm sorry, I can't mow the lawn. You're going to have to do it, honey. Could I learn how to run the lawnmower? No. That's just crazy. How about cooking?
The same. Harder for.
Same pattern, but look at the difference. It's like a difference in probits of 5. So you know what a probit is of like -10? That's basically 0. So there is like no chance that a woman of average ability can't cook. There's no chance of that. In men, there's a chance of that. So cooking is both more discriminating and much, much easier in women. So hard, I know. Now the rest of these, shopping, getting around, banking, using the phone, they're invariant. So yeah, I think you called it earlier, Zoomers, when you said these are the gendered tasks, right? Housework, bed making, and cooking are harder for men. So this is an example of where diff would potentially be informative, not a problem. So hear me out. Diff gets a bad rap because the idea of diff in education would be like, this item is unfair for people in this group, right? Because it takes something besides ability to get it right, and people in this group aren't getting it right as much, even though they have the same theta, and that's not cool. I agree with that. But think about this type of item analysis as being used to make a decision about an individual. If you are a clinician or a social worker or somebody who is in charge of like evaluating a person and making a decision as to whether you recommend that they are able to live independently, what this implies is that you would pay attention differently based on gender to whether they can do these items. So if you come across an individual who can't cook for themselves, and that individual is a woman, you should be very concerned. You should be more concerned than if that individual is a man, because cooking is harder for men. So the idea of, what's it called? There's a word for it, and I can't come up with it. It's an NIH buzzword, like individualized medicine or something like that. You know what I'm thinking of? What's the word? It's something like that. Zoomers, anybody?
I know what you're talking about.
Precision medicine.
That, yeah. Like, that idea that, like, you have to pay attention to, like, the whole of a person when you try to make evaluations about them. It's a good idea in theory, but this kind of speaks to that. So you might have different standards, sort of, for what is problematic behavior or a problematic lack of ability based on the gender of the person that you're talking to, based on other types of personal characteristics as well. Somebody who has arthritis, for instance, might not be able to do tasks that involve like fine motor movements, but they could otherwise probably still live independently. So if I find somebody who can't use their hands effectively, maybe, I send them frozen dinners in the mail, which is how I get my dinner. Or maybe, we hire someone to come in and just cook for them, but we let them do everything else themselves. So you might have like a different standard based on someone's medical profile, based on their gender, based on other types of information you have about them, that a diff analysis could inform. For this kind of person, this item is really important. For that kind of person, it's not as important. There are other measures of functioning in older adults. The mini mental status exam is still, I think, pretty widely used. And there's questions on there that have things like, can you draw a clock? And the other one is like, what year is it? And somebody could not be able to draw a clock if they have Parkinson's or if they have, any other sort of motor issue, but they could perfectly like understand what time it is. So that kind of thing. Question speaks to how we need to contextualize data, the why behind participants' answers. Yeah. Particularly if you're working with like comorbidity. So if you have someone who has like alcoholism and depression, right? Like the way they answer questions might be different than someone who just has depression. Or you might be more concerned about someone's alcoholic behavior if it's in someone who's not depressed or who is depressed. Like those sorts of comorbidity issues might color the way that people answer the questions, which would then cause you to make contextual decisions differently. So diff could be relevant. And so the solution that you could do, which would involve kicking out all the diff items, right? Would you want to do that? Like if you kick out all of the items that have to do with like taking care of yourself around the house, that's a big part of living independently. It's not just managing your money and being able to go shopping and stuff. So getting rid of items that show diff, I think would be misleading in this case, which is what people would do in an educational testing context, is get rid of all the items that have diff. So, items 2 and 7, the amount of variance that's not the factor is lower in women, whatever that means. In terms of trait differences, so in the reference group of men, our variance of theta is fixed to 1, and that's to identify the model. So both groups are on the same scale now. The men have a theta of 0 on average and a variance of 1. The women have an average theta of minus 0.38. And this p-value right here tells me that's significantly different than 0, meaning they're significantly lower. So the women for this sample are lower ability than men, but only with respect to the invariant items. All of the other items aren't contributing to this mean difference anymore because we freed them to at least some extent. Only the items whose thresholds are invariant are creating mean differences between the groups. So this mean difference of women looking like they're less able is somewhat misleading. They're less able when it comes to doing the stuff that's out of the house. They're more able when it comes to doing the housework. But those items function differently across groups. The theta variance is half of that. So it looks like the men are more different from each other than the women are. The women are more homogeneous. That's what this is telling me. And they are significantly less variable. That's what the very last structural test was revealed with the diff test. Is there a test of significant diff? That's what we were doing with the diff test at each stage. Is once you constrain the parameters to be equal, then you do a diff test model comparison to see if it hurt the model. Is that what you meant?
Yeah, but actually, for example, the item 3 seems harder for men than women. I want to know whether this hardness is significant or not. Is there something like this?
Yes. You could, I don't know if I did that in this case, but yes, what you would do is compare a model where the thresholds are constrained equal to a model where they're not. And then you could get a direct test just for that item 3.
Mm-hmm.
It would go in the opposite order of all the other tests because you'd have to start with the model where they're free and then compare it to the model where they're fixed.
Okay.
But there's an example of that in for the loading, the very first one that I did a test against the prior model. Here it is. So when I freed the loading for item 3, I went back and did it this way, where the free loading model is the analysis, the fixed loading model is the one that I estimated, and then the diff test told me that one loading needs to be free. So you could do the same thing for the thresholds.
Okay, thank you.
Sure. Another question, 1 second. How are we viewing homogeny in the groups such that what is it about the estimates? Where I am pulling that from, let me go back down to my final solution here. Here it is. I am pulling that from the fact that the factor variance is 1 in the men, and the estimated factor variance is 0.49 in the women. So women have like half the variability. And I know that those two numbers are significantly different because the very last test that I did was to make them the same and then see if the model fit worse. And so the chi-square test of about 11 tells me that those variances are not the same. So that is a structural invariance test at that point. And because I don't have any factor covariances, I don't have to worry about those. And the factor mean is already tested against 0 in the Wald test, so I don't have to do a separate comparison for that. So then I know that I have structural non-invariance in this sample. Women are both homogeneous and less able. However, I have to take into account the content of the items that were free, in which they actually are more able. Okay, did you have a question too?
Yeah, it's related to that. So in this case of the mean difference, that difference is related to the invariant items, right?
Yes.
Okay.
Yes. Only the invariant items are contributing to the mean and the variance. And so that's why I'm saying this mean difference is potentially misleading, because all the things that women were able to do more are not in it. They had to get free. All right, here's some pictures. So I took this final solution. Here's the code for it, by the way. This is my final measurement invariance model, where 6 of the 7 loadings are constrained and 15 of the 21 thresholds are constrained. And I re-estimated it, adding a whole bunch of labels so that I can convert those thresholds and loadings to A's and B's. So this is just a longer version of the code that you saw in example 6b. I had to make it longer because of the particular parameters that were non-invariant. You can't loop as easily. So I have, for instance, the discriminations go from 1 to 2. I skip 3 because that one was different. Then I can go from 4 to 5. For the difficulties, then I had to write the ones that were different separately. So that's why they have the loops with the different indices, because you can't go across all 7 if some of them are different. But what I wanted to do, though, is to describe how you would talk about these same relationships using IRT parameters, but to solve the problem that they were already going to be different because of factor mean and variance differences, I pretended like the factor mean and variance were 0 and 1 in the women. So it's not technically correct, but I wanted to remove that artificial difference as to why the A's and B's would look different. So like the thresholds are depicted graphically in this picture right here, where I have the submodels and the different colors. So we have the blue is the transition between an answer of 0 versus 1, 2, 3. Red is the transition between 0, 1 versus 2, 3. And green is the transition between 0, 1, 2 versus 3. And what the y-axis is here is the threshold, which is the probit of answering the lower option. And the dashed lines are for the women. So we can see that for the last threshold, that's where most of the non-invariance is, as well as for cooking. There's non-invariance for the other submodels as well, and a little bit on housework, bed making, and then these are all the same. Because thresholds are difficult to interpret, I converted them into B's, and that's this picture here. So after controlling for trait differences, these are how different the B's would be. So now the y-axis on this picture is the difficulty value, which is the amount of theta needed to transition with 50% probability into the next category. So for instance, if I look at cooking, for the last threshold, which is the transition from like can do it with some problems to can do it just fine, something like that, in the men, it takes a theta of like minus 0.25-ish to be able to make that transition. But in the women, it only takes a theta of -1. So it takes a lot less theta in the women to have a 50-50 shot of answering the higher choice. For the other submodels, though, the differences are not nearly as pronounced. So like for this last one, the blue one, this was significantly different, but it's not that different. So I could imagine, finding some way to express these differences as effect size or something like that would also be useful. But practically speaking, like how much theta you need to be able to do this, the biggest difference is in the green, the last submodel. That's where most of the data was anyway. And as usual, words. Lots and lots of words. All right. Other questions? Then very briefly, let me show you what it would look like to do invariance testing using full information maximum likelihood instead. This is the binary version of those same 7 items. So just simplifying things a little bit. This is example 7D. So rather than saying group equals, you have to do these 2 things under variable. The classes option asks for what variable you want to call your classes, and I'm picking the name group, and I want to have 2 classes. And then known class says, hey, how would you like to make the classes? Would you like me to make them out of the data, or would you like me to find them for you? If it's find them, then that's like a latent class or mixture model. If it's make them out of the data, then I'm saying, take this column where I've assigned people into either 0s or 1s and make that my group. So this is not a mixture model. It's just a trick. So estimator equals ML, link equals logit to be able to do it this way. And because it thinks it's a mixture model, we need these 2 extra analysis options as well. So we're using an algorithm equals integration, which is a different way besides quadrature to marginalize over the unknown thetas in the estimation process. The trick to setting up the models then, there's still only one model. There's not like model men, model women. There is this thing with, what is this? Percent sign? Is that what that thing is? It's above the 5. It's that one. M+ has used all the special characters on the keyboard at this point. They had left out 1 or 2, but they're now in version 8. So they've spent them all. They're going to have to like switch to wingdings or something to introduce new modifications. But we have this overall model in which I tell it how many men there are by converting the proportion of men in the sample into logits. Otherwise, this is going to become an estimated parameter that I don't want. Then for the rest of it, I have the loadings, the thresholds, the factor mean and variance fixed to 1, and then I have this group 2, %sign group, #2 %sign, and I will selectively apply the labels in steps of metric and in steps of scalar as before. Why didn't I do it this way to begin with? How am I going to judge fit? I got nothing here to work with. And if I don't have a saturated model to come back to, I don't have modification indices either. So the process of trying to figure out why your invariance model fits worse is a lot harder in this method. I have a configural solution here where I have latent class 1 with a 0 in parenthesis. What that means is that it's referring to female equals 0 from the known class option. Latent class 2 is referring to female equals 1. So men are the reference, women are the alternative. I wanted to point out something that happened in the output that I got no warnings about. This right here. Can you guess why I put exclamation points and put it in bold? You see anything like odd about the loading for item 4 in the women?
It's 10 probits.
It's 10 probits.
So it's a 100% chance.
It's
Or 100%.
a 1 unit change in theta is equal to 10 probits. But is it really 10? Look at the size of that standard error. Look at the rest of the standard errors. The standard error of 6, where everything else is like 1, it has no idea what this loading is supposed to be. It has no idea. So these sorts of problems may pop up when you use maximum likelihood that won't necessarily trigger error messages. But anytime you see standard errors that are like crazy out of bounds, then don't put a lot of faith in that parameter estimate. Now, why might item 4 have such a loading in the women? Just from the proportions, it doesn't look like that would necessarily be the problem. For whatever reason, it had a hard time figuring that out. Sorry, not diff, was looking above it. Yes, well, it was a different result. I'll give you that. So it does give you the IRT parameterization directly for binary items. So it gives you the A's and B's from the configural model. Then I go through and tried to test the loadings to be equal. -2 log likelihood difference was non-significant. So, all right, that's good. So then I go to thresholds, add the loadings on that. So I could do that by adding the labels, or I could do that by not writing them. Either way, I think works. And in this case, -2 log likelihood difference is very significant. So I'd have to go and figure out why. So I don't know which of the 7 thresholds is causing the problem. What I can do, though, is start by looking at univariate misfit. So this is output that I hadn't shown yet. This is from Tech 10. And Tech 10 gives you essentially the fit to the marginal probabilities. So how many people answered 0, how many people answered 1, and then how does the model recreate that? That's what we're looking at here. And the last column is a standardized residual for how wrong the model is. So for item 3, it looks like the predicted probabilities marginally are the wrongest. And so that would be a place to start, I think, in terms of which item thresholds might need to go. They're also off in the women, more than for other items as well. So that's what you would have to do, is go through and try to figure out which items are driving the non-invariance, but without the same easy tools to do so. So this is a potentially more painful process. But I wanted to show you an example of what the code would look like, but I did not go through and try to figure out what was wrong with it. I gave up at that point. But item 3, cooking, probably part of the issue here. All right, ta-da! We made it. I don't have to make another video. Yay. So that's all I have to say about diff and invariance, I think. Oh, no, I have one more thing to say. Wanted to give a shout out to moderated nonlinear factor analysis on slide 34. If you don't have groups, you can still do invariance. So what if you wanted to know if items work differently, say, as a function of age? And you had, like, between ages 3 and 10. Well, if these are kids of different ages, in order to make it fit into what we were just looking at, you'd have to make arbitrary groups of, like, little kids and big kids. And they're going to be arbitrary groups. Or you could just do invariance using a linear model for each parameter. So this is a technique invented by Dan Bauer. I have a couple papers about that on your reading list called moderated nonlinear factor analysis. And the idea is basically you hack M+ into fitting a linear model to predict each item parameter. So like you might have a loading and say that that loading is equal to some intercept, which would be the loading for the reference values of these predictors. And then beta age would tell you how different the loading needs to be per year of age. Beta group would tell you if the loading needs to be different in one group versus another. So the latter is exactly what we've been doing, just not in a linear model way. So he figured out that you could do this in a linear model way, which allows you to do multiple types of covariates at the same time, some of which can be quantitative, some of which can be grouping variables, as well as potential interactions. So there's an extra label of what variables you're using in this constraint that you have to identify in the variable section, but otherwise it works. And of course, there's an R package to do this that I found, and here's a link to that as well. That's all I wanted to say. There. Then the other slides are the ones that I had to draw because I was doing too much with my hands. We already talked about those. There. Questions? It's awfully dark. It's very ominous. Zoomers, any questions from you? Okay, is anyone going to be sad if I let you out 7 minutes early? I didn't think so. All right, don't be sad. Go home and enjoy your extra 7 minutes on me. All right, folks, thanks for being here. Have a good break. Go enjoy your friends and family, or go catch up on your sleep and your laundry, whatever you need to do. I will see you on the other side. Bye for now.